All right, this is a little intro to matter and energy in our food. So we've learned that organic molecules enter our mouth as food and look like this. And they move to our stomach and small intestine where they are chemically digested or broken down into smaller pieces. And then they travel to our bloodstream. So they have to be tiny to get into our bloodstream, where then they can travel to other cells and become larger molecules. For example, amino acids can link together and form proteins that make up our muscles or proteins that make up our bones and give them flexibility. So people are often surprised to hear that proteins are found in bones, but fat can also be found in bones, which is what my dog is consuming here. The yellow marrow cavity of bones is another place where we store fat in our body. But as you can see, not all food we ingest gets chemically digested. For example, we don't have the enzymes to break down cellulose, so it comes out whole in our waste, undigested. So now look closely at the typical cell. Count the number of glucose. 1, 2, 3, 4, 5, 6, 7. But then at time 6, you see only 4. So where did all those glucose go? Some of you might have said the glucose was turned into glycogen to store it for times when we might need it. However, if that were the case, you would see it in our typical cells, or in a muscle cell at least. All right then, so where is the glucose? And this should give you a clue, because a lot of times we'll say things like, oh, well, we burn that sugar for energy. What does that really mean, burning it for energy? Well, here, our marshmallow is quickly losing mass, but we know it's not disappearing. We know that it's being converted into carbon dioxide and water. And in your cells, that same chemistry happens. It turns into carbon dioxide and water. And so most of the waste of our marshmallow comes out of our breath in the form of carbon dioxide. So just to recap here, not all waste comes out of our bottom. So you can see here in our biochamber experiment where we have a burning marshmallow set up in a closed chamber with carbon dioxide and oxygen probes attached. The values show that the oxygen level is decreasing and carbon dioxide level is increasing. Note, oxygen is measured in percentage and carbon dioxide only in parts per million because there's a lot less carbon dioxide in the air. So here's our ATP, and some of you thought that when we break down sugar we use it to make ATP. Well, yes, that is true, but the atoms in sugar are not used to make ATP. When we make ATP in our mitochondria from using sugar, we basically have these starting molecules. We have an ADP and a phosphate, not chemically identical to this, but a simplified version. So all we're doing is we're taking the energy from breakdown of sugar and we're using it to put those together and make ATP. So there's no change in matter. The matter that was there is still there, and all we used from glucose is the energy available in those bonds. So let's talk a little bit more about energy. Okay, so this is a graph showing the potential energy in chemical reactions. We have on the y-axis the measure of potential energy, the reaction progressing here. And the reactants, for example, when we burnt the marshmallow, reactants would be glucose and oxygen. Our products would be carbon dioxide and water. So we had to light the marshmallow to get the energy started, to get this chemical reaction. This is called our activation energy. However, our products did not have as much stored chemical energy, and so energy was released or transferred, about that much. We call this an exothermic reaction because in most situations, some of the energy that gets transferred is going to be in the form of heat energy. Now in the marshmallow we had heat and light energy. In our cells, we do have some heat, we don't really have light energy, but we do take that energy and turn it into another chemical called ATP. Okay, so not every reaction is the same. In this situation, we have reactants that have lower energy than the products. So we had to put some energy into the system, and usually that comes from the environment. So we call that an endothermic reaction. Okay, notice the reading of the vinegar. It is at 22 degrees Celsius, and we're going to see what happens when we add some baking soda. Oops, obviously a bunch of fizzing. Okay, so the gas is being produced. You can already see a change happening here. Pretty quickly our thermometer has already dropped. Some bubbles, a good sign of a chemical reaction. And if you look at our temperature now, it's dropped down to about 18 degrees Celsius. And if you feel it to the touch, it actually feels pretty cold compared to the room temperature. So as you can see, this is an example of an endothermic reaction. So you may ask, if reactants and products and chemical reactions can have different amounts of energy, can our food have different amounts of energy? Okay, I have a marshmallow and a peanut. We're going to weigh these real quick to see what their initial mass is. The peanut is 0.5 grams. You can kind of make a prediction, or 0.6, probably between 0.5 and 0.6. Make a prediction of what you think the marshmallow will be. 0.8, surprisingly heavier. Okay, now we have the marshmallow on the scale weighing 3.0 grams, and we're going to light it on fire, try to burn as much of it as we can to see what happens. Some observations as it burns. We can light it one more time because there's a little bit of unburned part up there. And can we get anything more out of this one? Alright. So notice it burned pretty quickly, and probably we still have a little bit inside, but we had a slight loss in mass. Then we have our peanut here, weighing on the scale with everything else 2.9 grams. So we're going to go ahead and light this on fire, and I just want you to notice any differences you see in how this peanut burns. Okay, so you can see that our marshmallow started between 3 and 3.1 grams and ended at 2.9, so it only lost 0.1 or maybe 0.2 grams, whereas the peanut lost 0.5 grams, so close 4 to 5 times more mass. But did it only burn 4 to 5 times as long? No, I mean it burned significantly longer. So why does it burn significantly longer? So you can find this information on a typical nutrition label. If you look on the bottom there, it'll say calories per gram. Fat, 9 calories per gram. Carbohydrates, 4 calories. And proteins, 4 calories. So this gives you the total calorie content. So you can see 1 gram of fat would give us about 9 calories. 42 grams would give us like 168 calories. And our protein would give us about 28 calories in total. So overall, that'll add up to close to 200. Notice, though, that dietary fiber does not get counted because we cannot digest it. So one more time, carbohydrates have 4 calories per gram, proteins 4 calories per gram, and lipids 9 calories per gram. So what's really cool about organic chemistry is this can be applied to fuels. So look at where diesel is on this scale versus gasoline and ethanol. Now remember, all of these are originally organic matter that has turned into fuels, but ethanol we get from living crops today. We actually mostly harvest that from corn. But when you have ethanol added to your gasoline, it does reduce your mileage. So that's something we'll talk a little bit more about. But kind of wraps up organic chemistry and tells you why you maybe want to know about it. So this is the end, for now anyway. Thanks for watching.
Mom, could you please stop making that movie and come pet me? Please?